Okay, so our topic for today is power of Open RAN, 5G and beyond. Okay, so here is our chapter outline I prepared for you. So number one is the mobile wireless system evolution. So we'll just have a run through because we already discussed this in the morning. So we spend a lot of time today in this section. And then we'll have some short introduction, but this introduction will have some in-depth now, because in the morning discussion, it's just like a surface discussion in the 5G. And 5G complexity, why Open RAN can help in this 5G complexity, and the 5G private mobile network. So I will be introducing to you this new approach in deploying 5G and what is 5G and beyond. Okay, so let's have a glimpse about the evolution of the mobile communications. So from 1980s to year 2020, we have witnessed 5 generations of mobile communications in 40 years. So in 1980s, the first mobile communication, which is 1G, was released with the basic analog voice, no IP, almost 0 kbps in terms of the data traffic. The most famous network was the NMT, the Nordic Mobile Telephony, the AMPS, and the TAX. And in 1990s, the digital communications emerged in the entities of GSM. Okay, and then there is also the digital AMPS, the digital version of AMPS, and it has a digital voice, no IP at the first deployment until the 2.5G, which has a GPRS and EDGE. So GPRS means General Packet Radio Service, and EDGE is Enhanced Data Rate GSM for GSM evolution. So there is a counterpart for GSM in the areas or in the countries like Japan. This is the CDMA IS-95. But later on, the world adopted GSM and then continues up to the 3G in year 2000. So it introduces digital voice, the World Wide Web, and multimedia. The basic throughput on that time was around 2 Mbps, and one network for voice and other network for IP. So there's a separate entity or the different network, core network. One for CS, which is a circuit switch, and then one for PS or packet switch. So you have this CS core network, and then you have this PS core network. And the most familiar words you can hear here is the UMTS, the 3.5G, the HSDPA, high-speed data downlink packet access, and high-speed uplink packet access, and the HSPA Plus, and LTE. So LTE was introduced also in this time. So we have witnessed also the increase in bandwidth compared to the 2G in the 3G era. In the 2G, there was only 200 kilohertz bandwidth per carrier, but in 3G, the minimum bandwidth was 5 megahertz. Until such time that LTE came in, so we have different bandwidth. So we call it the flexible bandwidth. So the bandwidth for LTE, it introduces new frequencies, started from 1.4 megahertz, 3 megahertz, 5 megahertz, 10, 15, and up to 20 megahertz. And then if you want to increase more of your capacity, there's an option or a feature for an operator to use the carrier aggregation mode, which enables you to add another carrier coming from a different base station. So we call it the carrier aggregation. The 4G has a voice over IP capability. Unfortunately, they cut the CS voice here. So they replace it with voice over IP and voice over LTE. So this technology gives us around 100 Mbps as the minimum that time. And then right now we have an average data rate of 300 Mbps. One network for IP, so it becomes an all IP network, and it includes LTE Advanced, okay, 4.5G, and LTE Advanced Pro, okay. Now is the era of 5G, which is started in 2020. So we still have voice over IP, And then you can hear some different applications like virtual reality, V2X, like the vehicle to everything, and Internet of Things, which has right now our existing operators like Smart, Globe, and Dito have reached 1 gigabit per second in their test cases for 5G. It's also one network IP and originated from LTE Advanced Pro, and our technology is now. So during the evolution, as I continue, there is an evolution also in terms of the services. So from the 1G, since this is a simple design, so this is a basic service, is the analog mobile voice only. For the 2G, it's an improved service because you have a digital voice and more encryption. And for the 3G, there's a basic service as a IP connectivity to the internet. And then while the 4G is built for the MBB, for mobile broadband. So it's another improved service. However, for 5G, it becomes a complex system. Why it becomes a complex system? Because the services have been mixed up. So it includes, like, for example, the 3 use cases, the massive machine type communications, the URLLC, the ultra reliable and low latency communications, and the eMBB. So basically what we are saying about MMTC is that high data rate and then high capacity. When we talk about URLLC, it's the instant response of the network, meaning it's a fast latency of the network. And for the eMBB, that's the high throughput and high capacity. And for MMTC, that's the massive IoT. So multiple devices at one time. So up to 1 million devices per square kilometer. So because of these services, some mix up of services, the technology has been, the 5G technology is made to become complex in terms of the design as well. And then you will include the NR, the narrowband IoT, LTE, the Wi-Fi, and the satellite access. And later on, when 6G, if 6G will come, you will see some improved services in the 5G. So like, for example, enhanced MMTC, enhanced URLLC, and further enhanced eMBB, or further enhanced MBB. Okay, so as the evolution of the mobile communication goes to this new path, the more complex our system could be. Like, for example, in LTE, LTE Advanced Pro, so we call it an evolved LTE. So for LTE, a lot of things happen. Like, for example, we have the IoT, the Internet of Things, and then there was also a narrowband IoT applications, and LTE-M for minus, like for the minus category. And then there was also a licensing, LTE unlicensed. So you are using an unlicensed band, meaning utilizing the frequencies of the Wi-Fi. You also have this LAA, LTE license assisted access, in which it's a variant of carrier aggregation. So one carrier is licensed and then another carrier is unlicensed, like the 5 gigahertz frequencies, and then you can combine it. We call it the LAA. And then you also have the multi LTE Fire, LSA, and the CBRS in the US. We are also using more resources like the massive carrier aggregation. So it goes up to 13 carriers. You can aggregate 13 carriers for LTE under the 3GPP release 10 and the dual connectivity. The Wi-Fi access, we have resource allocation flexibility and direct connectivity like the V2X, D2D, and the PROS. So it becomes also complicated for in the case of LTE. There's a lot of features added and functionalities. In terms of the spectrum sharing, there is different entities in different countries. Like, for example, in the USA, there is a 3.5 used for CBRS, Citizens Band channel. And for the Europe, the 2.3 to 2.4. In Germany, 3.7 to 3.8 for private 5G networks. In France, 2.6 for private and public usage. And for UK, 1.8, 2.3, 3.8, 4.2, and 26 for shared licenses. And Finland and Australia, so national local subleasing for local operators. In the Philippines, we are not currently applying this spectrum sharing. So each operator has its own dedicated frequency. Unlike the US, like for example, the 3.5 gig operators are sharing this frequency. But in the Philippines, these frequencies are dedicated. They have a separate assignment for each entity. So what is network sharing? No? If we have a spectrum sharing, there is also called what we call the network sharing. So network sharing, we have three variants. So we have the site sharing. Okay, the site sharing is physical site sharing. Like for example, you have the core network. So you have a separate core network for each operator. Like for example, operator A and operator B. And then the radio resources like the G node B or the E node B, they share it. In one radio, both operators can share. But in this case, the site is being shared only, no, not the radio, not the radio. It's only the site. That's why it's called site sharing. And then they have their dedicated cell or frequency each other. So the only shared item here is the tower or the site or the infrastructure. Now we have the multi-operator RAN. So the multi-operator RAN, each operator has a separate core network, and in one radio, they can utilize the same radio, but using their own frequency. So that's what we call the multi-operator RAN. The multi-operator core network is look like this one is what we call the MOC-N. Okay, this one is MORAN, multi-operator RAN. This one is MOC-N. In MOC-N, every operator can implement it to their own radio access network. So what we are doing, for example, I am Globe. Okay, I am Globe. I will share my radio to Smart, and then Smart and Globe will use my radio plus my frequency. Okay, and at the same time, there will be a swap deal. Swap deal, meaning if I'm Smart, if you will use my radio and my frequency in one site, I will ask Globe to give me one site and allow me to use the radio of Globe and at the same time the frequency of Globe. So that's the multi-operator core network. So we can do it in the network sharing. This one operator handles the radio, but they are using separate frequency. But this one radio and one frequency is being used by both operators. So that's why it's shared. So in this sample, there is an opportunity for third-party vendors like the tower sharing company. So they could have their own towers. They can build the towers to both Smart and Globe. And at the same time, they could have a radio that is open if we deploy Open RAN that they will allow Smart and Globe to use not only the towers, but also the radio. Okay, so those are the concepts in the network sharing. Now let's go to the 5th generation or the 5G. So in the standards roadmap, so 5G actually started the initial studies in the release 14 in 2017, where they are defining the requirements. And then 5G phase 1 officially started in the release 15, 3GPP release 15. So the most immediate needs was the eMBB and the initial URLLC. And frequency is under 52.6 gigahertz. Release 16 is also known as the phase 2, where all ITU requirements like URLLC, MMTC, and V2X, unlicensed and satellite is already defined. Now there is a release 17, which is freeze in June of 2022, this year. So there was a 5G improvements like the NTA, higher frequencies, and integrated access backhaul. Release 18, also known as the 5G Advance. So the 5G Advance has a significant step forward, the eMBB versus the non-eMBB versus the cross-functional. So as you can see, as the 5G also evolves, the the features and the functionalities also evolves and become complex. So let's take a look at the 5G services, spectrum, and techniques. So you have these three use cases, the EMBB, the URLLC, and the MMTC. So you have two frequency bands, the FR1 and the FR2, the sub 6 gigahertz and the super 6 gigahertz. So this is also known as the millimeter wave. Okay. So 5G is the only technology right now that uses this full spectrum, bigger spectrum. So from up to 400 megahertz going to 86 gigahertz. 5G also can use the license shared, and unlicensed. Aside from that, for 5G, we have the millimeter wave and massive MIMO. We also have the flexible numerology. We have the CU and UP control plane and the user plane split, slicing, and the centralized RAN. We have the unlicensed satellite access, the device-to-device communication, and the vehicle-to-everything, LTE and NR integration options like the option 3X, the SON, the self-optimizing network, software-defined network, and network function virtualization. And when you look at this architecture of the 5G, the control plane is separated to the user plane. So the control planes are the following architectures, like for example, the network slice service functions, the AUSF, the access and management function, the session management function, and the user plane function. So the user plane function is the one handling the user plane for the data. So for example, you have a data network, you want to download something in this data network. So the data plane needs to go into the UPF, but the UPF is being controlled by the following control plane. So as I mentioned last time, if you want to get money from the bank, like for example, you want to do a withdrawal. So imagine that this is the bank where the money is stored. There's a vault inside. So before you get money going to your pocket, you need to go to the bank, show your bank book, and then show your credentials, your IDs, okay? And then check your balance, and then what is your maximum limit of withdrawal if there's a certain policy like that. And then before you make a successful attempt to get money from the bank. So it's something like that with the service-based architecture. When you look at the 3GPP split options as provided by 3GPP, of course, there is a stock 3GPP split options. So in the morning discussion today, so we have identified that there are 8 split options. So split 1, split 2, split 3, 4, 5, 6, and 7, and 8. So in the 3GPP, specifically in the Open RAN, so they are recommending the higher level split 3GPP in the ORAN, this in the split 2, in which the RRC, SDAP, and PDCP is like for example in the centralized unit, the RLC, MAC, and the higher physical layer would be on the distributed unit, and the lower physical layer and the RF could be on the RU unit or radio unit. So there is what we call the split 7.2. So meaning in the split 7.2, you will split your stock in between the higher physical layer and the lower physical layer. Okay. In the cases of a small cell forum, one of the proponents in the Open RAN, but more specifically on the small cells, they are focused on this split 6, where the separation of the MAC, high MAC and low MAC, and the physical layer is being done. Okay. So when you check on the 3GPP split options, so you can see here the split options, and then these the names, and then you can have the throughput requirement. So you can see here that when you do the split from split 2, 3, 4, 5, 6 up to the split 8 to the lower split, you can have this throughput requirement. Okay. So as you go on to the higher split level, lower level split in the split 8, so you can have a higher throughput like this. Okay. And in terms of the delay, you can also have lower delay in this split options. And in terms of performance, this is the mid performance, best performance improvement, and least performance. That's why in the case of Open Run, they are also recommending the split 7, where the optimal split can be utilized. Like for example, if you go for the split 7.2, you can design your massive MIMO antennas using this beamforming IFFT resource mapping in one AAU, in one antennas, active antenna. And then if you go for split 8, you can apply it in to not so complicated technologies like GSM and UMTS. But if you go for 4G and 5G, the 7.2 is the recommended split by the ORAN Alliance. Okay. So let's take a look at the logical disaggregation. Okay. Oh, sorry. Logical group. So let's go to the centralized unit. So this is where the non-real-time functions, the layer 3 and the higher level layer 2. So this is where the connection management, radio bearer configuration, handover, cell reselection and selection, data encryption, and header compression, and operation and maintenance interface and core. So you can see the centralized unit is divided into two. You have the centralized unit user plane, centralized unit control plane. Okay, so in the user plane, you have this SDAP, Service Data Adaptation Protocol, and Packet Data Convergence Protocol. The RRC, Radio Resource Control, is the connection or the connection between the UE and the BTS or the node EG node B. And then you also have the PDCP in terms of the control plane. You have this F1 interface going to the distributed unit. The distributed unit is handling the RLC, the radio link control, which handles the segmentation, MAC for prioritization, and the higher physical for the error correction. Okay. And now we have this ECPRI, which is an improved version of the CPRI. So in the remote unit, you have this lower physical layer in which the inverse fast Fourier transform is happening, and the MIMO and the beamforming, and also the RF in terms of the propagation into our antenna. Okay, so let's continue. So we also have this front hole, mid hole, and back hole. Okay, so since we have the DU and the CU split, there is a new transmission that was introduced. So let's start with the RU and the DU. So we still call it the front hole. And the DU and the CU will become F1 or the mid hole. And the CU and the core network is the NG back hole. Okay. So the front hole is the network between RU and the DU and can be a CPRI or eCPRI or IEEE 1914.3. So the front hole latency is around 100 to 500 microseconds. And the coverage between the DU and the RU would be 1 to 20 kilometers. Okay. And in terms of the services and latency requirement, in terms of the EMBB is 4 milliseconds, and for the URLC is 0.5 milliseconds. Now, the DU and the CU, it has a latency requirement for 1.5 to 10 milliseconds, and it can range, no? It can to be separated up to 20 up to 40 kilometers. So ganun siya kalayo. So what you can do, you can have the CU in the regional area. You can then put it in the data center, and then you can also serve the RU up to 20 kilometers. So that's how our system becomes disaggregated, okay, and centralized. So like, for example, you have the centralized unit here from 40 kilometers, and then the DU is located 20 kilometers, and you only see the RU at the cell site. So unlike the traditional network that we do, that you see the RRU and the baseband unit, and that's it. That's the cell site. Okay. But in the case of 5G, one cell site could mean, or 10 cell sites could mean one site, because it belongs to one DU and one CU. It's just distributed and centralized. Okay. Next, let's go to the 5G complexity. So what makes the 5G a complex network? First is naming architecture. So we have a lot of architecture in 5G. So we have this non-standalone and standalone mode. Okay, so if you have this kind of architecture, so it is named as like, for example, this is a standalone mode. So you have the NG user plane and the control plane in the RAN, and then you have these connections of N to N3. Okay. In terms of the dual connectivity, like, well, for example, the option 3X. So you have a different naming, like, for example, ENDC. So when you say ENDC, it's EUTRA NR dual connectivity. Okay. However, if your core network is 5G, you will call it, this one is multi-rat dual connectivity. Actually, this is the common term. If your core network is 5G, you call it the NEDC, NR EUTRA dual connectivity. And if you have this 5G core with LTE on that, so you have the NG ENDC. Okay, so NG RAN EUTRA dual connectivity. So there's a lot of naming convention as well, because you have a different options to choose from. Okay, from the, in terms of the architecture itself. Next, we have different naming for 5G and or the BTS. So for 1G, we call it the base station. For the 2G, we call it the base transceiver station. For the 3G, we call it the node B. For the 4G, we call it the evolved node B. But for 5G, we call it many names, a lot. You can call it EN G node B, NG E node B, G node B DU, if the G node B is combined with the DU, or the LSS, low level split G node B DU. So we have a lot of names compared with from 1G up to 4G. Next, architecture evolution. Okay, so the architecture evolution, we start from the 3G. From the 3G, the UTRAN is composed of the node B plus the radio network controller. So we call it the UTRAN. And then it's connected to the 3G core network. This is a packet. Okay, packet core. The serving GPRS support node and the GGSN. And then 4G came in. We removed the controller. Okay, we removed the RNC. And then we give the control to the eNode B. Okay, that's why in the EUTRAN, this two is merged into one, eNode B only. And then we separate the core network into control plane, which is handled by the MME, the mobility management entity, and the user plane, which is the control plane, which is the SGW, the serving gateway, and the PGW. Okay, PDN gateway, and going to the internet. Now, going back to going forward to 5G, you will see the CP split and the UP merge. Okay, the CP, the control plane, is being split into access mobility management function and the session management function. The session management function is the one that giving you IP address. Okay, and the access mobility management function for mobility and registration and control. Okay, and the UP is the user plane function. This functionality of PGW and SGW has been combined in the user plane, and then it becomes user plane function. So that's what has happened into the 5G core. And for the UTRAN, okay, for the NG RAN, it becomes split. So the eNode B, because we have this baseband unit, right? We have the baseband unit here and the radio unit. We split it now into two. We call it the centralized unit and the distributed unit. Okay, so that's how the 5G become complex in terms of the architecture. So when you compare it to LTE. So let's compare LTE and 5G, okay? Complexity. So for LTE complexity reasons, so LTE has been equipped with a lot of add-ons along the 8.3GPP releases. So there's a lot of add-on features, narrowband IoT, eMTC, license assisted access, okay, LWA, dual connectivity, vehicle to everything, device to device communications, carrier aggregation, coordinated multipoint, frequency division, MIMO, LSA, CBRS, and short transmit time interval. Okay, so there's a lot of add-on features. For 5G complexity reasons, so there's a lot of larger scopes, use cases to be covered. So you have the URLLC, MMTC, and the massive machine type communications. And set of technologies to be brought under the 5G umbrella. And then NR to natively bring LTE features with forward compatibility and flexibility as design principles. LTE will be part of the 5G, like for example, in the option 3X. So you have a dual connectivity. LTE is the master node and 5G would be the secondary node. But if you have these other options where the 5G is the master node, you can also make LTE as a secondary node. So that makes our network becomes more complex. And then if you look at the heterogeneous network, the HETnet, okay? So it's a big challenge for radio resource management of multi-rat HETnet. So how do you manage the resources? Because you have this dual connectivity, meaning the dual connectivity is that your phone is connected to different nodes. So it's just like carrier aggregation, but the other carrier is coming from the other PTS, and it is combined or split in the PDCP layer. However, the carrier aggregation is happening in the MAC layer. So you are combining a carrier with the same node, but it's happening in the MAC layer. You can also have the relay. Okay, so you can have a relay, you have the LAA, in which you are combining two frequencies. One frequency is licensed and the other frequency is unlicensed, like for the Wi-Fi. You have the LWA, you have the Wi-Fi, device-to-device communications, and the dynamic TDD. And in terms of the carrier aggregation, you have the frequency division duplex that you can combine with the TDD. So it becomes a heterogeneous network. It becomes a very big challenge in terms of the resource. How do you command each UE where to go and what cell to be used? Okay, actually you can do it by optimization, but when the network becomes very big, like a heterogeneous network like this, it becomes complicated. So we need to have a mechanism how to handle it. We need to have intelligence, okay, how to handle it. Not only a manual and manual human intelligence to see the performance, and then if the performance is not so good, change the parameter, okay, monitor for 24 hours or 48 hours. If the performance is not so good, change it again, try to make it trial and error sometimes. So it's not so what do you call this, efficient in terms of the optimization. We need further intelligence. So we need to maximize, or we need to get something from the IT world that they are using, which is what we call the artificial intelligence. Put artificial intelligence into the network. Equip them with artificial intelligence, okay, so that they can handle it. The artificial intelligence can handle this kind of complexity that human cannot handle in a long time. Okay. All right. So next is in the 5G as well, there is what we call the private network. Have you heard about the private network, private mobile network? So private mobile network is optimized or tailored LTE and 5G for industrial or enterprise use cases, like for example, industrial IoT. So maybe you have a client that owns a factory, that electronics company that they are creating, for example, IC chips or hard disk drive. or maybe an automotive industry that wants to connect their robots wirelessly. So they could have an optimized or tailored 5G network that could get from the operator. So when you say private mobile network, these are dedicated local network independently managed. So it has a carrier grade security and privacy, and it could either use a license shared, or unlicensed spectrum. And it could be owned by MNO, it could be owned by an enterprise, or it could be owned by a venue owner. So it is private. So we call it also the non-public network, the NPN. So we have different level options in terms of the private network. So you have the standalone, okay? You have the hosted by MNO, okay? You have the RAN sharing, and then you have the MNO slice. Okay, so later we will have a discussion on that one. So standalone, you have your dedicated network. You have your own core network, and then you have your own radio network. Hosted by MNO, so you are just leasing with the MNO. Probably you're just getting some over-the-air signal coming from the MNO. RAN sharing is that you have a separate core network from the MNO, and then you have a separate server or separate edge cloud that you operate, but the MNO cannot access it. So you have your own core network, but you share the radio. It's either the MOCN or the MORAN. So if you have your own frequency, we call it the MORAN. That's what we discussed earlier. But if you don't have the frequency and you have to share it with the MNO, it is called the MOCN. Okay, you have your separate core that the MNO cannot access, okay, but you share the frequency and the radio. So that's what RAN sharing is all about. And for the MNO slice, you have your own core network, and then you also get a slice of the core network for the services. Okay, so probably there's a service that the MNO offers you, and then you also have a server, dedicated server. So that's what we call the MNO slice, part of the network slicing. So why 5G fits here? Dedicated 3GPP features. So in the 5G network, so the private 5G network, so a spectrum license, a shared unlicensed, so NRU, and then you have the NPN, okay, so non-public networks. You have a unique ID, independent or integrated architecture. You have this high precision positioning for the industrial IoT requirements, and you also have this URLLC for high performance requirements. Like, for example, real-time automation, the movement of the arm of the robot. I believe you saw that previously in some videos in the manufacturing industries. And then you have the wireless control systems. This is flexible, scalable, and future-proof. So you can upgrade anytime you want. That's why it's scalable, high-performing, 3GPP supported, and optimized for local services. Now, under the 3GPP Release 16, the non-public network, so you have what we call the standalone NPN. Okay, so non-public network, meaning the NPN. So it is operated by a non-public network operator. So they are not relying on MNO. So access to public network possible. So as untrusted network, and subscription to one or more NPNs for UE. So we also have this public network integrated NPN. Okay, so NPN deployed with MNO support. Okay, so they are being supported by MNO. They have this dedicated spectrum. So it's also, they could get a slice, a close access, and group to disallow other UEs or UE subscription included. So they are not allowing other UEs to come on their network. So when you compare these two in terms of the spectrum, the maintenance, the SIM or the UE subscription, the security and the roaming and the expenses, so the standalone NPN has its own license. It could be, they could purchase their own license to, for example, NTC. It could be unlicensed. You can use the frequency of the Wi-Fi, but it's risky because you cannot control the interference, and it could be shared in cases of the US. For the public network integrated NPN, it uses the MNO spectrum. So you're just reusing the frequency of the operator. It could be unlicensed also, and it could be shared. For maintenance, you need an IT department. You need to have an integrator and connectivity provider. For MNO, it would be the MNO or the integrator that could do the maintenance. So these are the pros and cons, no? So a comparison. For the SIM and the UE subscriptions, the responsibility of the enterprise. And this one is the responsibility of the MNO. So the MNO is the one that will give you the SIM card. In terms of security, it is the responsibility of the enterprise because you're standalone. And this one is end-to-end security given by the MNO. Roaming, there is no roaming. For the public network NPN, integrated NPN, regular roaming. And for the expenses, initially you have higher capex because you need to buy equipment, okay, but lower OPEX because you're the one maintaining it. Okay, so you have your own integrator, you have your own IT department, so you don't have to subcon services to maintain. So you have a lower CAPEX. However, in the public network integrated NPN, you have a lower CAPEX because operator is giving you the resources, no? But you have higher OPEX because you need to pay the MNO for their services. Okay, so that's the difference between the standalone NPN and the public network integrated NPN. Okay, so private 5G network options. So we have this three. Okay. For example, you have this enterprise and then you have the MNO network. So we have this independent private network. So you have your own. Okay, you have your own network, you have your own frequency, and then you have your own core, at least the UDM, the CP, and the UPF. Okay, control plane, the UPF. And the MNO, you are separated with the MNO. So you're just a private entity, separate. You're an independent private network. For the RAN and signaling shared, so what is happening here is like this. You share the frequency of the MNO, or you have your own frequency, probably. You have your own frequency, or you share the frequency with the MNO, but you have your own UPF. Okay, user plane function is either a server in or edge cloud that you own that the MNO cannot access, but they can have a control. Or you also have the control will be handled by MNO, but the server is on your side. Okay. And the control plane, this one is controlled by the MNO, and the user plane, MNO is separated from you. Okay, so this is the RAN and signaling shared. For the network slice, okay, for the network slice, you will have part of the network slice of the network of the operator. So meaning when they give you the SIM card, they will give you an assignment, or like for example a DDN, like it's like an APN, access point number, no? The DDN, I forgot the data. I forgot the DDN meaning. It's like the APN. So it's a dedicated number for you. So whenever you access the network, once you access this kind of APN or DDN, so you will have this what we call the NSSI, network slice indicator. So you will get access to the network slice given by the operator. So you are also separated. You are still separated to the public network, but you are still under the MNO's service. So this is what we call the network slice. So there is a pros and cons of the 5G private network. So like for example, in the independent private network, so you have complete isolation from public network. You have an independent quality of assurance, you're secure, and then you have this local data storage. And then you have this low predictable latency because you control the edge cloud is located in your premises, so you have a predictable latency. and all components close by. And then there's no monthly subscription because you own the network. But the downside is you have a high capex in terms for software and hardware and license fee. So whenever you deploy something like a 5G or wireless network, you have to purchase your own software, and then there's a license. High spectrum costs. We all know that the spectrum is really high in cost, and if you use an unlicensed, you are prone to high interference and need for a skilled IT staff. So that's cons for having an independent private network. For the RAN, signaling shared, so you have this licensed MNO spectrum, so it's cheaper and less prone to interference. You have lower capex. Okay, MNO maintains the network with the service level assurance. It's secured and local data, and then low predictable latency. The downside is not completely isolated from MNO. So if you're very much concerned about the access access issues, so it will not be separately isolated to MNO. And then the signaling is dependent on MNO network. So if there's a loaded network or congestion, you will be affected. And then the subscriber info is stored in MNO's database. And then there's a monthly subscription, and there's a need for trained IT staff for troubleshooting. For the network slice, so you will have this logical separation from public network. So you're separated virtually. The spectrum is licensed to MNO. There's a low capex, and then the MNO maintains the network with SLA. In terms of the cons or downside is no physical separation from public network. It's only virtual separation. Dependency on the MNO network for QoS. So the MNO is the one giving the QoS, quality of service. And then you have a higher latency because the servers are located not in your premises. Subscriber info are stored in MNO, and then monthly subscription charges for end users or RAN storage, and need for trained IT staff and troubleshooting. So those are the pros and cons of a private 5G networks. Okay, so private mobile network. So before you decide if you're planning to have this private mobile network, so just check if who owns or manages the spectrum. So because this one is one of the motivating factors how to own a network. So if you have the spectrum, it's better. But if you're not owning a spectrum, just think twice, because if you will buy a frequency, it takes a lot of cost. Do you need the license or shared or unlicensed spectrum? And then what are your requirements regarding the capabilities and what needs to be dedicated? And do you need it with a single local premise or multiple premise or wide area? Okay, so these the considerations on the private network. Now that we all know that the 5G is can evolve under an umbrella of technologies like, for example, NR, LTE, narrowband IoT, where new features are added over time. There's a question that do we need next Gs or 6G? Because if you can just include the features, which is something like the 6G, don't need the 6G, right? We just need to evolve the 5G. Okay, but there's a lot of studies happening, like for example, in China, in University of Oulu, there's a 6G trial already happening, or 6G study happening. Although the 6G is targeted to happen by 2028 up to 2030. So the research for 6G is happening. Okay, so what will be the next approach? So in terms of the complexity, because the 5G is complex, right? So there is a comparison between the legacy of monolithic RANs and opening the networking in RAN. In legacy monolithic, when you say monolithic, your architecture is only one block, core and then RAN. But for opening the RAN, you are disaggregating your components from the hardware and component, and then you are decentralizing the locations of your hardware. Legacy monolithic RAN means a single network, closed interfaces, single vendor, and then you are based RAN limited, and RAN sharing. But for open networking in RAN, you will have the hybrid networks. So you have different integrated solutions. You have open interfaces, different vendors, and open initiatives. Like, for example, some XRAN or the vRAN or the CRAN or the ORAN and the TIP. And then you can also do the RAN virtualization, like what's happening in the Open RAN. And you can have this neutral host network, okay, and discuss. So the next approach in opening the RAN is from the closed RAN, okay, from the single vendor, monolithic vendor, vendor lock-in, best effort services. You can have this setup using the Open RAN. So you have separate RRH that you can mix and match with the BBU of another vendor, and then which actually this in the core network it's already happening. But if you apply in opening the system in the RAN, you can also do what you have done in the core network. So what is happening here? You can have flexibility in terms of there is a complexity that's happening. So the complexity can be handled by the RAN intelligent controller in RAN. So in terms of managing the resources, that's where Open RAN will help 5G. And in terms of the performance of the radio and software, for example, if you do not want the features that the existing vendors are giving to you, you can get it from other vendors and then have a mix and match with your current or the new system. So like, for example, in the RAN intelligent controller, there is what we call the X app. So the X app is like an application that you can delete or you can install in your RAN intelligent controller anytime you need it or anytime you don't need it. So that's how the creation of the task can be more efficient in terms of handling these complexities of the network. In the Open RAN, you will be using the commercial off-the-shelf or the COTS. So there's the virtual machines, containers, and then this is the container runtime. There's a hypervisor running on the Linux OS and running on the x86 or ARM commercial off-the-shelf hardware. Okay, so basically that's how Open RAN will handle the complexity of 5G. So with the promise of number one, we have 3 steps. We have 3 steps into opening the RAN. Number one is to open the front hole. So if we need to open the interface of each component. And number 2, disaggregate the functionalities from the hardware to the software. And after disaggregation, we do for the virtualization of the tasks and procedures happening and the functionalities. And number 3, and the most important, is giving intelligence to the RAN to handle these complexities. So we will let the intelligence of the RAN intelligence controller powered by the artificial intelligence machine learning to handle this new complexities offered by the evolution of our mobile communications in 5G. Okay, so to sum up our chapter summary, so mobile systems evolved from one size fits all to complex mechanisms supporting various use cases. And then 5G brings native complexity as it targets vertical industries and introduces slicing. And then private mobile networks are tailored for 4G, 5G solutions for specific applications with specific requirements. And opening RAN allows for breaking the G thing and feature-based evolution. Okay, so that ends our presentation for tonight. Thank you for your listening. And then if you have any more questions, let me know.